To start off with, we want to define a force. Kind of a just very general definition of a force is it's just a push or a pull on an object. We kind of have a good intuitive sense of forces. The one tricky piece that we need to add to it is the directionality of forces. Forces are vectors, so direction is very important. So let me give you an example. If we take these three people, let's picture that they're standing on ice skates so that they move easily. If we have this one person, force 1, pushing to the right here, and force 2 pushing here at an angle of 90 degrees, we kind of instinctually know that the person's going to go this way, but if we look at it in terms of vectors, it makes even more sense. That if we add these two vectors together, force 1 plus force 2 added together as vectors, we're going to get our total force, what we would call our net force, in this direction. So we're going to need something to sort of accurately depict what forces are going on here. It really, really helps to have a visual. That visual is a free body diagram. So let's just draw a very simple situation here where we have our object and we're pushing it this way. So we have some sort of push force. So F push. Maybe we have some friction associated with it, so our force of friction. We know we're going to have gravity pulling down on it, and maybe a force acting this way, so I'll call it maybe force 2. And those are all the forces acting on our object. This is an okay free body diagram. In terms of AP and what you're going to want to write on tests and things like that, you're going to simplify it even more. So you're going to have your object, and so let's draw it in red now, and your object is simply the dot. And all of the points come off of the dot. So force of gravity, push force, force 2, and your frictional force. Okay. Now, so this is a good free body diagram. This is kind of what's going to be expected of you on the AP test. One thing you want to keep in mind as you're drawing these, the other thing you want is for these arrows to be approximate to their relative magnitudes in terms of the force. So for example, if push force is bigger than frictional force, you want a bigger arrow for your push force than you do for your frictional force. If gravity and force 2 are about the same, then you want about the same size arrows for those two forces so that everything's, relative. You don't necessarily have to draw it to scale, but you want a decent depiction here, and that's going to help you determine what's going to happen to this object. So the first of Newton's 3 laws of motion is that a body at rest remains at rest, or, if in motion, remains in motion at a constant velocity unless a net force acts on it. So let's take, for example, our little sailboat here. Let's just say it's sitting in the middle of a lake, sitting still. If there's no force that comes to act on it, it's just going to continue to sit still and not move. A pretty simple, self-explanatory situation. The one that's a little trickier is, let's say that our boat is moving with a velocity of 5 meters per second this way. The wind pushed it up to that speed, and then all of a sudden the wind cuts out and it's gone, and we're assuming no frictional forces on the sailboat. So all of our forces are all of a sudden gone. The question is, what happens to the sailboat? Well, the sailboat is going to remain in motion at a constant velocity, so it's just going to continue at 5 meters per second unless something comes to stop it. Okay? So if it's already in motion, it's just going to simply continue that motion as is until another force comes on to change it. Newton's second law is probably best expressed in the form of an equation. We could say that the sum of all of our forces, and keep in mind those are vector forces, so I'll put a little arrow over it, equals mass times acceleration, and acceleration will be a vector as well. Our net force, which is kind of what this is saying add up all of our forces, equals mass times acceleration, the acceleration that object experiences due to those forces. Force and acceleration are always going to be in the same direction, or at least net force and acceleration are always going to be in the same direction. So that's kind of an easy thing to remember with vectors. The big key here, right, adding up all of our forces, this is a vector sum of forces. So for example, if I have a force that is 3 newtons this way, newtons is our unit for force, and then 4 newtons this direction, right, my net force here So the sum of all of my forces is going to be, right, do Pythagorean theorem or 3, 4, 5 triangle, 5 newtons, okay, not 7. So it's a vector sum of all of our forces equals our mass times our acceleration. So one kind of interesting thing to note here, right, if I put the same force on two different objects, so force and force, we'll call it force 1 and force 1 so that we know they're the same. And if I apply that to an object that has a large mass, then I'm going to get a small acceleration as a result. Or if I apply that same force to a small mass, then I'm going to get a big acceleration as a result. So for the same force, I can have two different outcomes depending on mass. So mass, we say, another way to think of mass is a measure of an object's resistance to a force. So if it has a lot of mass, it's not going to get a lot of acceleration in terms of the force applied. Or if I have a very small mass, it's not going to resist that force very much and I'm going to get a very big acceleration. Maybe an example here, let's say force 1 is 200 newtons and that's applied to a car that has a very large mass. It's not going to accelerate very far. But if you apply that same force to a smaller mass like a basketball, it's going to move much, much faster than the car is, or change its velocity much, much faster than the car would. Newton's third law states that whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. This is a very simple way of saying that forces act in equal and opposite directions. For example, let's say we have a floor here, and then next to the floor is a wall, so a solid wall. And then we have a box that comes sliding in, is going to hit this wall. So when this box hits that wall, it's going to apply a force on that wall. So force of box on wall. When that happens, the wall is going to exert an equal force in an opposite direction on that box. So this would be force of the wall on the box. And sometimes these are called action-reaction pairs. It's these forces that exist in a pair. And so the force of the box on the wall, the force of the wall on the box. Now, if you're going to do calculations with these, you do each separately. So you do the box and figure out force of the wall on the box and use that to calculate the acceleration that the box would experience coming off of the wall. If you wanted to calculate an acceleration of the wall, you'd use the force of the box on the wall to do that. So you're going to deal with them separately, but know that those forces exist because they're going to be very important to us here in a little bit.